Iron. Let's look at the element iron in plant metabolism. Iron makes up 5% of the Earth's crust. This is a phenomenal amount when we begin to think of how much iron is actually there, which means it is extremely abundant just about everywhere. It does not provide a deficiency overall. Goethite, which is alpha-3 iron oxide hydroxide, is the most widespread mineral in the soil. Hematite, which is an alpha iron 3 oxide, is found in well-drained tropical soils, which are oxisols and eudisols. These have soils that have been around for a long period of time without having undergone a glaciation, which would have peeled away the upper layers down to the bedrock. So these soils tend to be very deep. They tend to be somewhat problematic at times in nutrients, but iron is found in them to a great extent. Ferrihydrate, which is a hydrated iron molecule, is an important source for plants. These are found in most soils everywhere. The solubility of iron oxides and hydroxides decreases in the sequence. Iron 3 hydroxide amorphous is more soluble than iron 3 hydroxide in the soil. This is more soluble than gamma iron 3 oxide, ferric oxide, which is often called maghamite. This is more soluble than the gamma iron 3 oxyhydroxide, which is lipidochrosite, which is more soluble than the alpha iron 3 oxide, which is more soluble than the alpha iron 3 oxyhydroxide. You can see that there are different oxides, and these have a difference in solubility depending on which one you have in the soil. One may be more available than the other. The concentration of soluble iron in the soil is extremely low. We said that there was 5% in the Earth's crust, but that doesn't necessarily mean it's available for the plant. The soluble iron form are iron plus 3, iron hydroxide plus 2, iron hydroxide plus 1, and iron plus 2. What you get is if they combine with oxygen, or if they combine with hydroxides, they make iron hydroxides, which are insoluble. Therefore, you may have a problem with solubility depending on what your pH is. This is pH dependent. Minimum solubility occurs at pH 7.4 to 8.5. Now, if we think about this, most of the soils we talk about, we want it to be in a fairly neutral range, which would be somewhere between pH 6.5 to 7. Iron being available at the lower pHs is not necessarily a bad thing, whereas its solubility decreases up to about neutral. Acidic soil has higher available soluble iron, where alkaline soil has little. Again, it's not necessarily a bad thing because normally we don't like extremely acidic soils for plant growth. If we had a very acid soil, we might have a lot of iron in it. That could give us a toxicity problem. Waterlogged soil reduces iron plus 3 to iron plus 2. Iron plus 2 has a greater solubility than the iron plus 3. Remember, paddy soils are waterlogged, and because of that, they tend to create an anaerobic condition. Many of these anaerobic bacteria do anaerobic respiration, which means they are taking other ions other than oxygen to receive electrons when they're making ATP. Iron is one of these. Again, iron may cause toxicity if we've got too much of it. This part is extremely important and interesting. We have what we call chelates. Chelates are molecules that are going to help something become more soluble. Iron readily forms organic complexes with chelates or siderophores. We're going to take a look at the difference between the two. A chelate is a compound containing a ligand, which is typically an organic compound bonded to a central metal ion at 2 or more points. So chelates are extremely important in plant mineral nutrition or in the mineral nutrition of all organisms. A ligand is an ion or molecule attached to a metal atom by coordinate bonding. This means you've got these molecules which have the ability to grab something at 1 or 2 places, which tend to allow for a larger molecule that might be more readily absorbed. So these are important as well. We use ligands in a lot of different forms in biochemistry. Siderophores, on the other hand, are a molecule, notice it says secreted by a living organism, which bonds, solubilizes, and transports iron. A siderophore works only on iron. If it is secreted by a living organism and binds, solubilizes, and transports something else, it is not going to be considered to be a siderophore, but rather it's going to be considered some sort of chelate. So we need to look at the difference. A siderophore is secreted, it bonds, solubilizes, and then transports iron. Chelates may include compounds such as citrate, oxalate, and EDTA. Citrate is secreted by all organisms. Oxalate is produced by most organisms. EDTA is a chemical that is manufactured that helps solubilize different materials. Therefore, we are going to use these in order to solubilize things. Chelates are very important compounds that are therefore useful to us. This shows you calcium EDTA. Now, I'm not going to go into the whole name of it because it's absolutely humongous. But one thing you see is the calcium on the inside. And the calcium is hooked up to nitrogens and to oxygens. It is bound on the inside. It is held in more than one place. But calcium EDTA becomes very soluble and is easily picked up by plants. You can do the same thing with iron, manganese, or other materials that might be of questionable solubility at any time. When we look at iron, beginning part solubility sources, where does it come from? How do we get it into the plant? All of this comes together with these particular chemicals.